We saw through examples that it is not always the case that N1P space of a metric measure space produces desirable class of functions. For instance, when the space had no rectifiable curves, this N1P space ended up being equal just to the usual LP space, from which we cannot expect any desirable properties of Sobolev functions. For example, that they have absolute continuity property along curves, or they are continuous and have density points on more than just LP functions. On the other hand, we saw that for Rn, N1P of Rn with the usual metric and measure does equal, up to representatives, the W1P classical weak derivative definition of Sobolev functions, and then all these properties listed here do hold for them. So whether the N1P space produces an interesting class of functions or not depends on the metric measure space. No surprise there. But can we find out which spaces will produce a nice N1P space? And the answer has been again and again proven to be what is called PI spaces. These are probably the best and at the same time most general class of metric measure spaces on which N1P has many of the expected properties from what can be called Sobolev functions. We will see examples of these, and we will see why this is not just a restrictive amount of assumptions on a space. We can have PI spaces with non-integer Hausdorff dimension. We have PI spaces that are subsets of Euclidean space and yet have no manifold points and no interior, in fact, no open ball sits in them. So still they are a huge class of functions, and we do have many nice properties for Sobolev functions N1P on them. And this list is just a quick recall of what we mean by desirable properties for a class of Sobolev functions. We want that class to be Banach space, which is always true, in fact, even without PI. But properties like 2, that we want better integrability for functions, and having quasi-continuous representatives, and of course being absolutely continuous along almost every curve, will not hold in general, and PI spaces is the right setting where this happens. So in this video, I want to define what we mean by a PI space, and compare the N1P space also to the high-wash space. And later I will let you know that I have already uploaded a whole sequence of lectures regarding Poincare inequality, and I will show you where to find them. So without further ado, let's recall some definitions. We call a metric measure space is doubling. This actually involves the measure, so we can also call it measure doubling if there exists some constant C such that this constant will be bigger than 1, in fact, for every ball in X, so let's call it ball, the measure of twice the ball is not much larger than the measure of just the ball itself. So this constant C controls how larger the measure of the enlarged ball can be with respect to the original ball. So here's some ball in the space, and then you look at the same center, so 2b, or in general, as we will need soon. So lambda b means ball with center as that of that of b, but radius lambda times that of b. As you can expect from Rn, because the measure of a ball, the Lebesgue measure of a ball, is proportional to r to the n, so 2r to the n is 2n r to the n. So the Lebesgue measure on Rn is 2 to the n doubling. We can call this c the doubling constant. If there are multiple c's in a listing of properties of space, we can have this index d for doubling. So one of the criteria to be a PI space in definition is to have a doubling measure, and this is what is meant by that. This 2 here is really not that much important, because you can actually use that to also find a bound on 3b, and usually there are, even if you have balls that are not exactly sharing the same center but are nearby, you can again do some adjustments in larger one to contain the other to still be able to compare their measures. This condition is a bit weaker than being Alfors regular, which would say that the measure of a ball of radius r be proportional to r to the alpha for some alpha. If you have this property, clearly you can see that it is doubling, but the converse is not always true. And what is a PI space? So P is between 1 and infinity, only 1 inclusive. We say a space, a metric measure space, supports a P Poincare inequality if, and I'm following for conventions and definitions and the results that I will mention, the monograph by Juha Heinonen, Jeremy Tyson, Nagiswara Shanmugalingam, and Pekka Koskela from 2015. And you can consult there for precise statements and proofs of many of the results that I will soon mention. So according to them, their definition in that book, which then you should have in mind when reading all the proofs and statements, is this. We say it supports a Poincare inequality if there exists some C and there exists some parameter lambda such that, okay, so I already forgot to include some small yet important detail that, so first of all, we want that measure of a ball be positive and positive and finite for all balls in X, and the more important part, the inequality part, is that there exists some constant C and lambda such that for every function u from X into R that is integrable, that means L1, on all balls. So you could say that the function is locally integrable or integrable on all of space. There are subtleties in defining it this way. I don't want to get into there. So for now, I'll just say that this is just to guarantee that our integrals will be well defined. So integrable on all balls. So for every such function and every upper gradient, which we have defined, various instances, gradient rho of u, we have, well, this is the Poincare inequality part. So the integral average over ball of u minus integral average of u over ball. So first you integrate u on the ball and divide by measure of ball to get this one number. And now you integrate this quantity against the du mu measure. Again, the integrability on all balls guarantees that this is well-defined quantity, and we want it to be less than or equal to c times diameter of the ball and this quantity. So the p appears now here, 1 over p, and then here we put integral average of the upper gradient rho to the p, and here we integrate over a slightly larger ball, so lambda times b, we dilate the ball lambda times, so this is slightly helping the right hand side. So we say that the space has the Poincare inequality p Poincare if for every u and every upper gradient of that we have this inequality for all balls b subset of x. So a big definition starts here all the way and ends here, and well, it's a long definition, but everything comes down to this inequality, and all other small assumptions are just to make sure this is well defined. For example, the fact that we require the measures of the balls not to be 0 is to allow us to divide by measure of the ball to take average. So a PI space then, as I mentioned above, a PI space is doubling and supports some p Poincare inequality. So these are the promised nice class of metric measure spaces. So let's code some results without, of course, any proofs. These are often difficult to prove results that make my claim more clear of why these are such nice spaces. For example, we have, I don't want to write theorems because I'm not going to be super precise and list all assumptions. So I'm going to make them facts. In PI spaces, Lipschitz functions are dense in N1P. Okay, that was one of the not desirable properties. So some of the claims will hold under other more additional assumptions, and those are usually not like too much. For example, some of the results are true if we assume that our space is complete or that it is geodesic. Being geodesic, well, seems very strong, but actually it is true that, let's write it here. So PI spaces are quasi-geodesic. So they are almost geodesic. We've seen this geodesicity before. this quasi-geodesic means that there is a universal constant so that any points x and y can be joined by a curve whose length may not be d of xy, but up to this constant of quasi-convexity is less than the constant times distance of xy. So it's almost close to being quasi-geodesic, and in fact we can redefine the metric to turn it into a geodesic space. So other common assumptions are being proper, so that you want the closed balls to be compact in your space. So some of these claims, facts that I'm listing, will need one or two of these additional assumptions. The other fact is that in PI space, so when I say PI space, I often think some specific P parameter is fixed. So N1P functions are P quasi-continuous, a concept we have not yet defined because it requires some other definitions and tools. But just heuristically, it means that the function is actually quite nice, not just on complement of null sets, but on complement of often much smaller sets. The other fact is that in PI spaces, the N1P, okay, since I've been repeating this, let's do it again. In PI spaces, N1P happens to be equal to M1P, the high-wash Sobolev class. And this is actually quite surprising and a strong claim, because the way these two spaces were defined is extremely different, where N1P was defined through upper gradients and behavior along the path. M1P is defined globally, and the high-wash gradient is a global LP function. So this equality, for example, says that the high-wash functions actually have upper gradients and they are absolutely continuous along curves, which is amazing in that direction. On the other hand, there are properties for M1P that follow easily from definition, and under this inequality, those properties then hold for N1P functions, which from just their definition is not clear. For example, density of Lipschitz functions in them. The other property that we expected and liked Sobolev spaces to have is that they are more integrable than expected. And those are covered under the name Sobolev-Poincare inequality. So in a metric measure space, so Poincare inequality, Sobolev-Poincare inequality in Rn, remember, has this exponent that if you are in W1P, then you are P star integrable, which is Pn over n minus P. Notice that there is this no dimension n of Rn appearing here, so we need some parameters from the space to state these, and that is actually used, the parameter that is needed or is sufficient is that you have some lower density on measures, so that if you have two balls, probably B prime contained in B, that this relative measure is bounded up to constants by diameter B prime over diameter B to the Q. And this Q is used in place of that dimension N. So this one requires some more assumptions on the space. So let me go back to my list and check. we showed that in PI spaces, well, we had this already, being Banach was done, Sobolev, Poincare, Lipschitz functions are dense, we mentioned, quasi-continuity we mentioned. Absolute continuity along curves, well, is not really because it's a PI space, it's simply how N1P spaces are defined. And the list actually continues. A lot has been studied about PI spaces and is still being studied. There is also the story of differentiability of Lipschitz functions on PI spaces, pioneered by Cheeger, but we don't have the necessary background to go into them. Okay, now back to where to go from now, or where we arrived here actually. I was surprised to see that we have already 40 videos on analysis on metric spaces. There is a playlist under this title. So what happened previously was I defined some basic definitions like being a geodesic, being a length of space, and having doubling measure, which I did repeat its definition here. So there's multiple videos on that, and then I talk about Poincare inequality under different definition where we didn't yet have any notion of upper gradient or even had not defined any Sobolev class. There we defined the Poincare inequality through Lipschitz functions, whose definition really doesn't require any measure. So we would have that this inequality hold up to a constant for Lipschitz functions, and here we put the Lipschitz constant, or pointwise Lipschitz constant. And then we talked about examples where Poincare inequality holds and doesn't hold. We mentioned how the smaller p is, the more connected the space has to be to support the Poincare inequality. For example, we had this two squares touching along one point, and we saw that it can have a Poincare inequality only if p is bigger than 2. It is true, just by Hölder inequality, that if you have a p Poincare inequality, then you get p plus epsilon Poincare for all positive epsilon. So going up is no issue. Therefore, the less trivial Poincare inequalities are when you want the smaller optimal p. Okay, we had some videos on them, and then we defined the Hajwas-Sobolev class, talked about it over several videos, and then I showed you how to get that Rn has one Poincare inequality, the best Poincare inequality possible, as a consequence of estimates on Rees potential. Okay, so let me show you where to find those videos. Again, go to analysis on metric spaces playlist, and if you sort them by date added, you can go all the way back and find those videos. So examples of metric measure spaces, Poincare inequality for a sequence of diamonds connected along vertices, Euclidean functions, Hajwas-Sobolev functions. I talked about Hardy-Littlewood maximal function on just general doubling spaces. Okay, and that was the first kind of series of lectures on analysis of metric measure spaces. The more recent ones, as you can see the switch in the pictures, is that then we start talking about Newtonian Sobolev functions. We talked extensively about absolute continuity along curves and what it means. Then we talked about upper gradients and constructed the Newton Sobolev functions in lecture 9. Okay, and then recently we had been talking about very specific examples of Newtonian functions. For example, we talked about what Newtonian functions look like on the unit interval and then also on the infinite line. The lecture here, number 11, I mentioned that to study further the N1 p-spaces, one needs the two notions of capacity of sets and modulus of path families. Those definitely are on my agenda to talk about at some point. Maybe modulus is my favorite because it also appears in some other aspects of my research recently, and it's just a very nice tool originally coming from complex analysis that has applications elsewhere as well. So until then, I will probably encourage you to go back to the videos on Poincare inequality. And now that you know how significant it is for the theory of Sobolev functions, have a look at them and let me know what you think and where else should we go from here. Thanks for watching this. Probably it's been a long video, but I appreciate your patience. Have a great day.